In this segment, we'll finish up the optimization of count inversions, introducing a couple of more sophisticated cache optimization methods. The prior segment cut out half of the cache misses by improving spatial contiguity of the data, arriving at count versions 2.c, which will be our starting point for this segment. Now, the optimization required to cut down on the remaining cache misses is more sophisticated. The reason we get so many cache misses is that for each vals I, we traverse all the remaining vals j values. And this causes long runs through the vals array, which runs create a series of cache misses. After incrementing I, we retraverse almost exactly the same run of vals j values the next time, less 1. One might hope for some help from pre-cached data at that point, but the end of the prior run will long since have booted the start of the run out of the cache, so the new run starts afresh with new cache misses. The cache just isn't big enough to store all the tags in the array at once. And question 1, how many pairwise comparisons of a vals I and a vals j will we make, given num hogs of 10,000? And how does that compare with the cache miss count for line 28? Well, returning from the pause, it's going to be about, give or take, 10,000 squared divided by 2. Actually just shy of that, but give or take 50 million. And so it matches very closely with the cache miss count of just over 50 million. In other words, each pair is causing a cache miss. The vals I value stays cached during the line 27 through 31 inner loop in count inversions 2.c, but each new vals j access causes a new cache miss. Now, if the core problem is that the cache can't hold an entire run of vals j values without losing the first ones, perhaps we need shorter runs. What if we group the loops differently? Imagine the entire array of 10,000 cache hogs broken into sets of perhaps 20 cache hogs each. Would we be able to compare just the cache hogs within each set with minimal cache misses? And question 2. The critical question is whether all the data needed for one cache hog set would fit in the cache. So assuming a set of 20 cache hogs, how big a cache would be needed to be able to load the entire set into cache at the cost of one set of cache misses, and then to work entirely in cache for all of the roughly 20 squared divided by 2, or 200 or so comparisons within the 20 cache hog set. Now remember that cache won't load an entire cache hog if we're not accessing most of it. Cache loads only the cache lines needed, not the entire C data structure. Assume a cache line of 64 bytes. Returning from a pause, each cache hog will take one cache line for its 2 tags, but nothing more than that. So we'd need 20 times 64, or about 1,280 bytes of cache. Well, even the 8K byte cache on this ancient processor we're using can manage that. So we can do the 200 comparisons within each set of 20 cache hogs at the cost of 20 cache misses, and that cuts the miss rate from around 100% to around 10%. But what about between sets? There are 10,000 divided by 20 is 500 cache hog sets in the array if we divide it up that way. Most of the comparisons are between cache hogs in different sets. Between any pair of sets, there are 400 cache hog pairs to be checked. So let's look at this diagram here where we've kind of rough diagrammed the idea. We have 10,000 cache hogs broken into sets of 20 each, and there's an ellipsis here between the beginning and the end. So let's imagine that we start with set A, say perhaps the first one, and we begin by doing all internal comparisons in A, and then we do all comparisons with A and each following set in their entirety, all 400 of them, before moving on to compare A with the next set here instead. And again, we do all 400 comparisons for that one. and then move on to the next pair. Now, given that we'd already have set A cached, we would incur for each following set another 20 cache misses, but then we'd be able to do 400 comparisons back and forth in cache, assuming that both sets fit in the cache at the same time. Now, 20 cache misses divided by 400 comparisons is 5%. That's even better than the 10% we had for the intra-set comparisons. The method is called loop tiling, and the sets are termed tiles. An alternative and somewhat uglier term, by the way, is strip mining, which it's also called. Now, we'll use tile instead of set for each of these things, henceforth. Loop tiling requires a rather sophisticated cascade of nested loops, with the outer loops driving through all the tiles, and here as well, and then inner loops driving through the comparisons within each pair of tiles or inside of a particular tile. With the right loops, there's no need to actually break the array into pieces. Looping carefully within the array will work. Now, conversions 3 fill, .c has a partial implementation of loop tiling, as you can see here, with tile size left as a input variable so that we can easily experiment with different tile sizes. And so we come to question 3 here, which is a fairly significant one. I'd like you to fill in the rest of countinversions3 fill.c without consulting countinversions3.c. Compile it and get it working. A few notes here. The big for loop drives through the tiles with ibase and ilim giving the bounds of each successive tile. The line 31 through 37, missing loop, does intra-tile comparisons, compares within the I tile. The line 40 through 49 loop goes through all the tiles in the rest of the array after the I tile, with JBase and JLim giving the bounds of a second tile. Now, don't worry if you find the loop tiling doesn't improve the speed yet. It will after we do some tweaking in the following discussion. Think on this then, and we'll look at the solution in countinversions3.c when you're done. So, returning from a pause that probably should have taken you a bit of time, the solution I came up with, as I mentioned, is in countinversions3.c. You can see that the loop on 31 through 37 here is doing intra-tile comparisons with just ibase and ilim, and then the big loop 40 through 49 is going through each of the succeeding tiles and then comparing it against the contents of the I tiles. So we're using ibase and ilim and jbase and jlim here to do the inter-tile comparison. Now, a similar pattern will work for any nested loop computation that needs cache optimization. So we have a new rule. Cache optimization rule 3. Use loop tiling to group nested computations so that they fit within cache. Now, the first two rules dealt with spatial contiguity. This one deals with temporal contiguity, rearranging code so that the uses of a given memory location are closer to one another in time, so that the location can stay cached for multiple uses. So let's try out our new loop-tiled implementation. In question 4, before we do so, what tile size would be appropriate for an 8 kilobyte cache with 64-byte cache lines? Now, leave a little room, by the way, for other variables like I, J, ilim, jlim, and so forth. Coming back from a pause, well, we have 128 cache lines. And if we reserve 120 of them for the tiles and assume that each cache hog needs just one cache line, then we can keep 2 tiles of 60 cache hogs each in cache. So we try out the code with a tile size of 60. And nothing. We're still at about 50 million cache misses. This is cache grind 3.txt, by the way. I didn't bother to put you through the misery of watching the thing run. This is the output available in the course materials. Okay, so maybe we miscalculated. Let's try it with a smaller tile size, maybe more like 8 or so. And I have for that cache grind 3a.text, which was run with 10,000 and a tile size of 8. And that one produces 53 million. Well, this is irritating. So what's going on here? It's almost as if our cache is a lot smaller than we thought, and indeed, that's effectively what's happening. So get ready here to use all that deep cache architecture we learned in the prior segments. Question 5. Consider the cache size of 8K, cache line size of 64 bytes, and associativity of 4. Now, how many cache sets are there? Coming back from a pause, well, there are 128 cache lines and therefore just 32 cache sets. Okay, question 6. Now consider carefully the size of a cache hog. How many different cache sets will be used by accessing tag 1 and tag 2 from each cache hog in a contiguous array of them? To which cache sets, in other words, do all the tag fields in the array map? Coming back from a pause there, well, cache hogs are exactly 1024 bytes long. So each pair of tag fields in successive array elements is 1024 bytes apart, or 1024 divided by 64 is 16 cache lines apart. They map to every 16th cache set, which is a 32 set cache means they'll all map into just 2 cache sets. So we're hitting just 1/16 of our cache, a total of 8 cache lines in 2 cache sets. It's as if 15/16 of the cache weren't even there. So let's reality check that. Trying a tile size of 4, so it could fit 2 tiles into this putatively 8 cache line area. Running with 4 here, that we finally get an improvement. It's 22 million, so it's just a 50 to 60% reduction of cache hits, but at least something's happening. And the reason it's not better is that with a tile size of 4, we're getting 4 cache misses to load each tile with just 16 pairs between each set of tiles. So it's a 25% cache miss rate regardless. Plus, at least some of the other variables also need cache, and they're probably hitting the same cache sets that our tiles are overusing. Now the fix is to stagger cache hogs so they don't line up so neatly. It's that binary-powered length of a 1024 that's creating what we might call binary resonance between the vals array and the cache. A simple fix would be to add a dummy 16 bytes or so to the end of each cache hog to break this resonance. And doing so, in count inversions 4.c, we will find, when we run it, 1 million cache hits. Much better. That's a rate of about 0.5% for that line in question, and 0.2% for the program overall. That's about as good as it gets. And running the program, we will find an execution time of 0.424 seconds. Now, that sure beats the almost 7 seconds or so we started with by a factor of around 15 times. And it's all due to reorganizing for cache efficiency. Based on this, let's add a fourth rule. Cache optimization rule 4, break up binary resonance. And note that this last rule, and the diagnosis that led to it, requires a full understanding of cache architecture, as well as knowledge of the cache parameters for the machine under study.